This week's lesson is on the science behind Ethernet.
Welcome. It's great to have you all here with us. The lesson today is going to be about Ethernet. And if you think that that's a really cool way to catch fish, then you need to keep watching because you need to learn about Ethernet. This is a networking technology. And we're going to be talking today in today's lesson about the basic introduction, but then coming up next time, we'll be getting into the really juicy stuff about Ethernet. So get ready for that. Well, a little bit of science news. NASA just launched their Artemis 2 SLS rocket, along with the Orion spacecraft that's up on top of the rocket. And this is the beginning of a 10-day mission where they're going to fly, 4 astronauts are going to fly out all the way past the moon and back and land safely back on Earth. This is a mission getting them ready for what they're hoping in 2028 with Artemis 4, where they're planning to land on the moon for the first time in a lot of years. So it's really exciting how that program's coming together. So keep an eye on that. Well, it's time to get it over to Dr. Joshua for How to Study with Acellus Gold.
Today, I'm excited to tell you about a brand new initiative that's just coming online. You know, a lot of parents are on really tight budgets and are paying the monthly tuition for Acellus Academy to make it available to their families, especially in families with multiple students. Those monthly tuition payments can really add up. And Dr. Billings has been looking into ways that we can help families that have a hard time making those tuition payments. And you know, it doesn't seem fair or right that parents should have to pay for their kids' schooling twice. You know, parents pay their tax dollars to fund education, but then they pay the tuition again to enroll their students in Acellus Academy. And so Dr. Billings has been working on a program that would allow us to help out some of these families and help with that tuition cost. And so this brand new initiative is called National Cyber School, and it's something that's just coming online where the parents and the students get all of the benefits of Acellus Academy, the ability to choose the courses and access to Acellus Gold and the parent support, but the costs are picked up by the student's local school district. And for some families, this might be a program that would really help to make it more accessible. And so if you want to check it out and learn more about it, go to acellus.com and scroll down to the section of the website with information on National Cyber School. We're just getting the program up and running and working with districts. You can go and find out if your district is already participating, and if they're not, you can request to be put on a wait list to be notified once they do, if they begin to offer the program. If we see in areas where there's quite a bit of interest, we plan to even reach out to the school district and see if it's something that could be made available. So we're hoping that it will help more and more families to make Acellus available. Thank you very much.
All right. Now it's time for Breakthrough Moments in Science with Tobias.
So Ethernet. I'm excited to talk about the Ethernet. Now, talking about the Ethernet, we get to learn about an electrical engineer, okay? And we're going to jump right in and meet Ron Crane, okay? So he was an electrical engineer. Now, here's a nice picture of him there. Let's jump back, though, to when the story really starts in the 70s. Oh, yeah, there we go. And he'd gone to MIT and to Stanford, and now Ron was, in 1974, he was joining the company Xerox, okay? Now, immediately you might start thinking printers, but a lot of things that Xerox was doing was involved with computers as well. Well, When Ron comes on the scene at Xerox, he learns about an initiative, a project that some people were doing at Xerox, okay? So there are a couple people especially that were spearheading this. One was Bob Metcalf. I love this picture. This is kind of like one of those pictures, like, hey, Bob, what? Like that kind of picture. But Bob Metcalf and then one other guy. So there's Bob on the right and then David Boggs. And these two gentlemen and some other engineers at Xerox were trying to accomplish a connection between computers. Now, this is the 1970s, so they're trying to get computers. You know, if you have a computer back then, you maybe could do some stuff on it, but how can you communicate with other computers? And so their idea was something that other companies had already started working on of, could we connect computers together? And they drew inspiration from some installations like ARPANET and AlohaNet. And so they thought, well, let's create a way that we can connect computers together so they can share data between them and printers. Like if we had an office and there was one printer and lots of computers, what if they could all print to that one printer? Now to us today, that's kind of like, yeah, that's how it is. Well, back then it was not. So they were working on a system to connect computers together in what we would call a network, okay? So Ron starts learning about this idea they had, and they actually had a name for it too. The connection, the wire system for these computers, they had nicknamed kind of the ether, which was an old science term for kind of this mysterious space connection between like celestial bodies like planets and such. And so they called it the ether. So Bob showed Ron some of the stuff they had done, the ether and the Ethernet, right? And so as they showed Ron the setup, it was pretty rudimentary. It was pretty slow. They couldn't send the packets and the information very quickly, and it was pretty buggy. And the connection wire that they had chosen to use as the data wire, okay, was a coaxial cable. So something kind of like this, okay, something some people might use to connect their TV, to get the TV on their TV screen. And so this was the cable that they used. And so in the middle, you had the copper wire inside and then all the stuff around it. And so they had one of these going down between the computers. And then at each computer, they had another one of these that connected to the computer, and then they needed to connect that to the one running in the middle. Now, there was an issue, okay? And it was that the printer will only get one connection, one wire. So how are we going to get all of these different computers to all share connection to the printer? So they did something called a vampire tap, and it's like what it sounds. They took the middle coax cable, okay, and they used a vampire tap, which it would literally puncture that middle cable, and it would make contact to the copper wire inside of it. And so each computer would tap in through the vampire tap. This is great, ether, vampires. And that way they could all connect to the printer. Well, when Ron looked at it, he started digging into kind of how they were, the system that they were using, that they had created. And so he worked on making it a lot cleaner and getting it hopefully to run a lot faster, because, if you're going to have something that a lot of people are going to use, you want it to move kind of quickly, right? So as he started working on this, he helped refine it, and they could get up to speeds of like 2 megabits per second, maybe 2.5. And Ron was able to take that, and he improved it so much it was more than triple the speed. And they got it up to 10 megabits per second, which was like unheard of. And they started connecting systems together through the Ethernet system that they made, where they could make networks of these computers. And they would eventually get up to 100 computers all connected, and they could share. And there were some limitations compared to what we have now. But eventually, Ron would go help co-found 3Com, the company 3Com, and they would release the EtherLink card. And this was the first commercial Ethernet network interface card. And if you look on it, there's that silver connector out there on the end that's connecting to that coaxial connection point. And eventually they would be like, hey, we need to get a better we need a better cable system for connecting. So then it starts getting familiar where they started using twisted pair cabling. And you had multiple wires inside and would become what we know now as, if you hear someone say, hey, do you have an Ethernet cable? That's more of what you would think of, right? So beyond that, though, Ron Crane would go on and he would get involved with the IEEE and into standards, and Ethernet would become standardized, and different speeds, and the system would then spread into more of what we know today, where Ethernet is kind of just something we almost take for granted every day. But this would come, from this little beginnings with these vampire taps and this ether, all the way to something now that's literally changing the world. And it's behind the scenes of basically all the networks with this Ethernet. And so if you come into something and it's a little rudimentary, stick with it. And through science and engineering, you might just push it out to the world. Thank you.
All right, and now it's time to hear from the proteges.
Today, we're talking about Ethernet. Without Ethernet, the internet would look something like this.
Oh, bro. Come on, I have a high score. Bro. Oh. So what is the big idea behind internet? It all comes down to two computers talking with each other. We've talked before about transistors and how they can store ones and zeros, and that's how computers basically store information with their own special language. But what if we want to get this information from one computer to another?
Well, back in the 1970s, scientists actually came up with a protocol called Ethernet. This is how computers would talk back and forth with each other. Here's how it works. Say we have two computers that want to talk to each other. One of them is going to send something we call a packet. You can think of this like a letter.
When you write a letter, you start by writing the name of the person you're sending it to. That's exactly what we do with a packet. We start by sending the name of the computer we're sending it to. But in the world of computers, their name is a unique number called a MAC address. So the first part of the packet would be the MAC address of who we're sending this packet to.
Then we write the source MAC address. This is like signing your name at the bottom, so the person you're sending it to knows who sent it. Next up is the type. This tells the person that we're sending the package to what kind of data is inside of the packet. You can think of this like what language you're writing your letter in. If I sent it in Spanish, I would need to read it differently than if I sent it in English.
Next up, we have the actual data. This is the real message you're sending. Then lastly, we have the frame check sequence, or the FCS. This is like a special checksum at the end. It lets the receiver check if the packet got damaged or changed during the trip. If the math doesn't match, the packet gets thrown away and sent again. So now that they had this new Ethernet protocol, they wired up two computers using a type of cable called coax, and now they could send these little packets of data from one computer to the next.
So let's imagine this. We have two computers and they're connected through a wire. We want to send data between the two. So we will listen to the wire, see if the other person's sending anything. If they're not, then we go ahead and we send our data. But what do you think happens when both computers listen to the wire? Nothing's happening, so they both send their data. You get something called a collision. And when a collision happens, no one gets their data. So then we have to try sending it again, and we send it again, and we send it again, and we're both sending it, and no one gets anywhere.
And then this got even worse when they were like, but we want more than just two computers on the line, so we'll throw on another and another. So these are all on the same cable, meaning if I sent a packet for him, anyone else could still pick up that packet, but they would just ignore it because it has his MAC address on it. But you can imagine how many more collisions would start to happen at this point.
Hey Caleb, how are you? I'm good.
Yo,
How are
Alvin,
you?
what's up?
Alvin?
What?
Good.
What's up?
How are you?
What?
The Phoenix Square Pacer test is a multi-stage aerobic capacity.
So you can see there were a lot of issues with these collisions that we needed to fix. So how'd they do it? What they ended up doing is they started having, if you would get a collision, you would wait a random amount of time and then resend your data. So both people are waiting a random amount of time, and then one of them sends, and then the other one sends. And that's how you could still get your data.
And then the next thing they improved was the type of cable that they were using. So they switched to a type of cable that you actually might be familiar with called Cat5. And inside this cable, there's 4 twisted pairs of wires. Now, a fun fact, who do you think invented twisted pairs?
John Cena.
Huh? It was actually Alexander Graham Bell, clear back in the 1800s. And he invented this type of wiring because in his telephone systems, he had wires traveling a long distance that would pick up some interference. And he found that with these twisted pairs, he was able to filter a lot of that out. So they switched to this Cat5 cable, and they also switched the layout. Instead of having one big cable like they did with the coax that all of the computers were hooked up to, they switched it to a star layout where they have a hub in the middle and Cat5 cables going out to all of the computers. This had a few advantages, and one of the main ones was that if a cable went out, now it would just be one of those cables going to the computers, and just that one computer would go down. Whereas before, with the coax system, if that cable got cut or broke or something, everyone would go down. So this was a bit better, but there could still be some collisions in the hub where all of those signals from all the computers met up.
And eventually we would work through these problems and improve on them further and further until now we have over 2 billion computers and an estimated 200 zettabytes of data all traveling through the internet. And now we can access all sorts of things, like even ScienceLive.
All right, now it's time to get it over to Dr. John for the Technology Spotlight.
This is pretty exciting. You know, usually I get to cover the latest and greatest. Well, today I'm still going to cover the greatest, but it might not be the latest. I'm going to tell you about some of the technology that was developed at WideBand Corporation that I got to help with that was able to solve some of the problems with Ethernet. Remember those collisions? It's actually a bigger deal than they explained in their protege video because those collisions really slow things down. And the more computers you have, the worse it gets. And it makes a limitation on the size of the network because it takes a certain amount of time for the packets to go across. And so you listen, there's nothing there, but then the packet's already coming. So it's a really, really big problem. And we developed a way to solve that problem by making it so when the packets come to that hub, we replace the hub with something smarter. And we call it a concentrator. And what happens is the packets come and they're going to crash. And instead of crashing, one pauses for a second while the other one goes. And that way, you can have the high performance without the collision. And it means you can use more of the bandwidth, so you get higher performance, and you can not have to do the retransmission stuff. The CSMA-CD is what they call it. And so it made a huge difference for Ethernet. I want to tell you a little bit of the story, though, because imagine you had this great idea, everyone's having these collisions, and we just need to solve it, you know? So that's the easy part, thinking of that, but then how do you actually do that? And the short, really important piece is a FIFO. And I have a nice complex diagram to show you what a FIFO is. Okay, it's not that complex. So it stands for first in, first out.
And this is a term that's used for a lot of things, but it's used specifically in this case for a type of memory. And so if you look at this diagram, one guy's loading stuff in, those are the packets, into the FIFO, and then the other guy is pulling them out of the FIFO on the other side. And the thing that's really special about this is it doesn't matter that they're loading and unloading at the same speed or not. One guy could be putting them in faster, and the other guy could be pulling them out slower, or it could be the other way around. And as long as the FIFO doesn't get full, then everything's happy. And so we used a special chip that had a FIFO in it. And this is what it looks like. And the idea is the packets come into the FIFO, they get saved, and then when we're ready, we pull the packets out. Now, if nothing's going on, there's nobody already sending, then we pull it out immediately and send it. But if something's going on, then we wait for the packet that's being sent, and then we send that one. And so that allows us to do that thing where the two packets come and one waits while the other one goes. And that simple thing made it so Ethernet is so much more efficient. And you don't have the same limitation on size of the network. And it made a really big difference. So I want to walk you through a little bit of how this works, because I think it's really neat when you start to understand it. So we have the FIFO, but before we can get to the FIFO, we have to have the data coming off the wire. And that data is serialized. Serial means one at a time. And so they take the ones and the zeros and they use those pairs to do a differential signal. And I want to show you a little diagram that kind of helps us understand it. See how there's the red and the blue lines? And in one condition, it's a 1, and the other one's a 0. And then down at the bottom, it shows the actual results. 1 or a 0, 1 or a 0. And as those signals change, then it determines the ones or zeros. And that happens really, really fast. So we have a special transceiver that takes that and serial data and then turns it into several signals all at once. And we call that a bus. These are different signals. And those are slower because we take the serial line that's coming really fast and then we spread it out over the 8 signals. And I guess to be exact, we use a special 8B, 10B encoding. I'm going to cut out some of the complexity to make this a little simpler. So then we have the transceiver run it in straight into the FIFO. The thing about the transceiver is it has data whenever the data is there. And if you don't read it out and save it, then it's gone. And then you lost the packet. That's what a collision is, right? And so you have to have that right. So then we made the board, we made the concentrator, had everything on it, and then we tried it. And then we debugged it. And how do you debug something that complex with all these little chips on it, with all these high-speed signals? It's a really interesting experience. You have to use something called a logic analyzer, and you take all these little probes, you got to be able to see really well, and you connect them onto the pins, and then you hook it up to the scope, the logic analyzer, and you can see the waveform of all those pins and figure out what's going on versus what's supposed to be going on and figure out how to fix it. And so that was what we went through in order to get this working. And the missing piece that I haven't told you about is the chip in the middle that tells the FIFOs, okay, you send, okay, you send, okay, you send. And now that was a special chip that didn't exist, so we had to make it. We used an FPGA to make that. And here is one of the very first concentrators. And oh, this is like history in my hands, the beginning of the Ethernet right here. And while everyone was working on trying to figure out how to get it faster, they were trying to get up to 100 megabits, which would be like 100 million, right? We were looking at a gigabit, which is 1 billion bits a second. And so this is much faster. And again, because we have no collisions, that works. And so you can see here is that FPGA chip, and then here are the FIFOs. How about we look at the picture really closely? If you look at this big one, I'm going to
show you the picture here. This is the same board. And then I'm going to zoom in and circle something. Those are the transceivers. And you'll notice how they're little circles. That's because they have heat sinks. Because these have that really high-speed serial signal, and they get hot. And so we have to cool them down. And then, right after the transceivers, we go into the FIFOs. Remember, these are the first in, first out, so it's saving that packet data if we need to wait. Otherwise, it goes straight through. And then finally, it goes up to the control chip, the FPGA, that we custom designed. And that is the process that goes. And this one sends it back out to the other ports. Okay? Now, I want to zoom way in on these little teeny components right here that you can hardly see. Luckily, I have a close-up. This is the equalizer circuit. This is really cool because it makes it so the serial signal is readable all the way across the long wire. And it's really interesting physics how if you have more ones or more zeros in a row, then it changes the signal, and you'll have either really big signals or really, really small signals to see. And the equalizer normalizes that so we can actually read the signal on the other side of the wire. In fact, the technology that we used worked a lot better than a lot of the Ethernet of the time, which is really, really impressive when you think about that we were going faster. Now, if you look carefully at this board, you can see some little add-ons. And when we started making these boards, we had machines, robots that could build the boards, but we didn't have robots that could make the boards. So we were soldering a lot of these parts on by hand, which is really fun, but there's a lot of parts. And so it's interesting. But in the very first prototypes, we had to make a few adjustments on our circuit boards, and we didn't want to have to buy them. So by the fixes on the circuit board, so we had to put them on by hand. You can see these special fixes for the link. I want to zoom on one of my favorite fixes on this board. You can see it's right over here. And you can't tell unless you look really carefully. These are those little popcorn parts, and they're actually stacked on top of each other. And this is to fix the link circuit where it detects that there's a link. And it's a whole tangle, we used to call it the rat's nest, of all the wires there. And I was not the best at putting that fix in, but we had some people that were really good at it, and it's quite a challenge. And again, this was until the next version of the Concentrator board came out that we made a lot of, and we shipped them all over the place, and it was very, very good at streaming video. Nowadays we think, you know, streaming video is normal, right? But back then, people would say that it wasn't possible and it was never going to happen. You're never going to stream video because it takes too much bandwidth. It causes too many collisions. And WideBand, I believe, is part of what changed that story, which is really, really neat when you think about it. And so it was a lot of fun to make a whole bunch of these, and we did get the robots to build them, thank goodness, because we made a lot of them. And one of my favorite memories of this project was what we call debugging. If you've done STEM 2 or STEM 1, you know how much I like to call debugging like being a detective, right? So you take on the challenge, and I would send data over the concentrator and see what happens. Sometimes it wouldn't send at all, or it wouldn't turn on at all. So that would be a hint. Sometimes most of the ports would work, but there'd be one port that doesn't work. And sometimes it would link, but it would only send data, it wouldn't receive data. And so it's like a mystery novel, you know. And so you get all the clues and you got to figure out. And then you pull out the probes, the oscilloscope, and you start testing the pins and everything. And then when you solve it, you feel really good about yourself. You know, like, we got it. And sometimes it was really easy. Sometimes it was really hard. And I want to show you one of these components again. This is the transceiver. And sometimes we would get a little bridge of solder between two of those pins under the part where you can't see. And so the only way you could know is by tracking it down to figure out which part it is. And then we had some tricks to try to pull solder out of under there to clean that out. And those hidden bridges were really tricky. But the hardest one that I remember trying to solve was when the parts were fine, the soldering was fine, but the circuit board had a bad trace in the middle of the circuit board. And so the only way to know was to probe the different pins, look at the signal, and then figure out which pin didn't look quite right and track that down. And then, special rework, we were able to make that work. And so it was a lot of fun to be able to work on the early versions of internet that paved the way for what we have today. And later we worked on even faster and better stuff. I'm going to tell about that a little bit later, so I guess that's all the tech we have the time for. Thank you.
And now I'm pleased to introduce the host of Science Live, Dr. Roger Billings, along with co-host Paige Monet.
Ooh, look how tall I am.
Yeah, right. Just a minute. Oh, that feels better, doesn't
so
it?
small.
Well, hello, everybody. Hope you're enjoying this wonderful day. And what fun we're having. We're learning about networking.
We are.
And networking's a lot of fun. A while back, we talked about the Billings computer. And it was one of the first. And it caught on. We made a lot of them. And it was a big thing. Well, eventually, I sold that company. And so then I ran into problems with networking. And with Ethernet, it was a great thing because all of a sudden you could build a local area network and you could hook up all the computers in your business so they could share information, talk to each other, and talk to the printers. Fun fact, in the early days of the Billings computer, this would be like 1977, 78, we had the Billings email system.
Yeah?
Yeah, and that was early. We had the Billings word processor, which became WordPerfect, but we also had the Billings email system. And to be able to email, you had to hook computers up to each other, and Ethernet was still trying to be invented. So the way we did it is we'd pick up the telephone and we'd call the person we wanted to send the email to. Hi, Peter, I got you an email. Are you ready? Okay, go ahead. He says, I got to load the program. He had to load a program on his computer. Then we'd both take the phone and we'd stick it into a thing called a modem. We'd stick the handset in on both sides. And then the computers would talk, beep, 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 and we could transmit data at 9600 baud. Well, that was in the later part. We started out at 300 baud, 300 bits per second. And if you divide 300 by 8, then you know how many characters per second. So it was kind of slow, but it was neat that you could do that. But now with Ethernet, we could do that at 10 million characters per second, which was a big jump. And so we put it in our company. We'd started the International Institute of Science and Technology, IST. Mm-hmm. And we had a lot of computers, and we're hooking them all up onto an Ethernet network. Our coax cable expert down there that built our network is here with us tonight. Kim, it's good to see you. Yeah, remember that? The network would go down, and they'd call her, and she'd come in and just twist the connector, and it would work again. Yep. Remember that? Yeah, it was special. But here's what we ran into. When we got more and more users, and at the times they really needed the network, they started to have collisions. And when you start having, you have more and more and more, and it get heavier. And so it would go from 10 million characters per second, or 10 million bits per second, which is about 1 million characters. It would go clear down to sometimes none. And the network would just die because everybody was trying to send at the same time, just collisions, 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 collisions. So at the time when the network was under the most pressure, it worked the worst. I thought, that's backwards. It should work the best when everybody's trying to send, not the worst. It's kind of like, you know, the big freeways in Los Angeles. Right when they really need the freeways, rush hour, the cars aren't moving. And hopefully they stop before they had a collision. But it's the same kind of a concept. So I said, there's got to be a better way. And of course, my first idea is, if the network was faster, then there would be much less problem. And so we started talking about it, and the guy said, well, maybe you could go 100 megabit, 100 million bits per second. I said, nah, if we're gonna do it, let's do it right. See, this is the Bill Lear training. Bill Lear taught me, when you go for it, go for the gold. Who wants a silver medal? Go for the gold. I said, let's go for 1 billion bits per second. And everybody said, oh, you can't do that, but let's do it anyway. And so we did. That little circuit there, the equalizer that he showed you, I spent so many hours working on that crazy thing. And if you really want to study, it's like a tone control on a stereo. And what that equalizer does is it changes the tone or the strength of the high frequency signals compared to the low frequency signals. When you're sending data, you're going to have somewhere it's going to be 10, 10, 10. That's the highest frequency. If you send 1, 1, 1, 1, 1, and then 0, 0, 0, 0, that'd be low frequency because it's not changing very fast. Well, we would put the data into the wire at 1 volt. And on the other end, it would come out at about 0.8 of a volt. So we had a little bit of wire loss on the low frequency parts of the signal.
What do you mean wire loss?
Wire loss, that's signal loss. The voltage went from 1 volt clear down to 0.8 of a volt.
Okay.
But on the high frequency components where it was 0, 1, 0, 1, 0, 1, we only got 1,000th of a volt.
That's a little bit.
There was basically no signal, just barely nothing. And that's why we couldn't send it over a twisted pair cable. And so that was killing my whole project, my whole company. I started this wideband company. We're going to change networking.
I remember that.
And we were all ready to go, except now we could only use about a 10-foot cable. And it's hard to get all those computers into a room where the cables are only 10 foot long.
Very hard.
And so the standard for 10 megabit was you could go 100 meters or 300 foot, the length of a football field, right?
Right.
And so wrestled with that thing. I wrestled with it. I tried to figure out how we could boost just the low frequencies, but we'd have to boost them almost 1,000 times. That'd be 1,000 volts. We couldn't do that. And so then I got this crazy idea. If we can't get the high frequency to be high enough, loud enough voltage, what we should do is we should make the low frequencies be low too. Okay. And so that little circuit with all those little components that you saw, they're all just resistors and capacitors. It tuned the low frequency signal down so that when it got to the other side, it was 1,000th of a volt. And it didn't touch the high frequency signals, so they stayed 1,000th of a volt. And with all the signals coming into the 1,000 volt, we could amplify the whole amount and then go 100 meters,
really
which was
impressive.
pretty neat. It was kind of fun. But that wasn't enough. The real problem with Ethernet was those darn collisions. And when they were all using the same wire, you can see why they had to collide. It's like if they're all going on the same freeway, it's going to get bogged down. So why don't they go on different freeways? And I got thinking, you know, if we could keep the freeways running at 70 miles per hour at rush hour, we get a lot of cars through. Mm-hmm. The problem is at rush hour, they slow down to, sometimes they just stop. They just park and read the newspaper there on the, you know, Highway 5. Anyway, I wanted to get rid of the collisions. And the problem is somebody's going to transmit at the same time. Well, they all had their own wire coming into the hub. So there was no more collision in the wire. It was all happening in the hub. And here's this electronic unit in the middle, and it would get signals from anybody and send it out to everybody. That's all it would do. And I thought, What if we made the hub smart? What if we had it receive the signals, and when it received them on the different wires, it stored them up. Johnny told you about the FIFO. It's a kind of memory that fills up, and it will hold them until you're ready for them. And so if one's sending, you just buffer them. And when the channel's free, then you send them out. You never lose a single byte. You never have a collision. And I thought that would be really, really, really cool. And so we came up with the idea of the Concentrator. One of the guys that I explained this to, a guy named Bernard Daines, who went to the same university I did, got all excited about it. He had a company called Packet Engines, and it was interesting. For 3 hours, he told me why it wouldn't work. And then at the end, he says, you know what, Roger, this is an amazing breakthrough.
That was a Comdex, wasn't it?
It was a Comdex.
Yeah.
And then at the next IEEE Gigabit networking meeting, I got there a little late because I was flying into California from Kansas City. And when I got in there, Bernard Daines was up talking to everybody, telling them about his new invention, a buffered repeater, which was my invention. And at that moment, when I was ready to, I remembered what my mother taught me.
Oh, yeah?
You see, before I learned to be social from Paget,
Yeah.
I was mentored by a wonderful mother, and she made me memorize poetry. And one of them really came in handy. She said, when others are praised for the work I do, I will work some more and praise them too. And I walked in, I heard what Bernard was saying, and he looked down at me.
And he went quiet.
And he saw me, he just went white. And I went, it's a good idea, it's a great idea. And he sat down. Well, anyway, it's fun. This guy, Ron Crane, that Tobias told us about, was an amazing inventor out of MIT. He had a PhD in physics. He also studied at Stanford. But at any rate, he'd come in, and he's the one that figured out how to do all of that over the coax. They'd tried, but he made it work. And I had an opportunity to meet the vice president of this company, 3Com, that had revolutionized networking and brought out Ethernet. And in fact, his name was John Marmon, and he actually came to work for WideBand Corp.
He sure did.
And on one of my trips to California, he said, how would you like to meet the real inventor of Ethernet, Ron Crane? I said, well, I'd love to meet him. So you were there, weren't you, on that trip?
I was there. We're in Sunnyvale, California.
So we went to Ron Crane's office in Sunnyvale.
Yeah.
And I just was so thrilled to meet this legend. This guy is amazing. He's the one that really made Ethernet a reality. He's what I would call the keystone inventor of Ethernet. And so I could hardly wait to tell him I've figured out how to get rid of collisions. And so I did. I said, Ron, at wideband, we've done something amazing. We're going fast, but we've also eliminated all of the collisions. Do you remember what he said?
He says, you can't do that. He said, Ethernet is collisions. Ethernet is collisions.
And I said...
And he didn't say it like that.
How'd he say it?
It was much more forceful.
He wasn't social.
he was very passionate because that was like his baby. That
very
was what he
offended that I was messing with his technology, wasn't it?
That was the right word, offended.
And I said, but Ethernet really, as a standard, was a lot about how you recover from a collision.
Right.
And I said, you can still recover the same way, except you don't have any to recover from.
He's like, no, no.
Then it wouldn't be Ethernet. And how'd that end up?
Well, after a good hour of two very brilliant gentlemen going at it, and then John Marmon sitting there thinking, what have I done? I have introduced these two. Then Ron, my goodness, what have you got?
Then he realized what it meant, didn't he?
Yeah, and he was all in. He was all in.
And he became one of my best friends. And
it was a very heated
that
conversation.
very same Ron Crane came to my New Year's Eve party that year.
He did.
And then he spent most of the rest of his career, he passed away a few years ago, but he spent most of the rest of his career working on hydrogen.
Yeah.
So warning, if you come here, Don't get hooked on hydrogen. I mean, do.
Oh no, it was like Clash of the Titans.
It was a lot of fun.
It really was.
Well, it turns out that being a friend of Ron Crane is really important to what happened next.
Yeah.
But just so you'll show up next time, I'm not going to tell you till next time what happened, because
It's a good story,
he did
though.
something really amazing. But with this concentrator technology, or as Bernard Daines calls it, this buffered repeater instead of a hub, we were able to build very, very fast networks. And we weren't just going 10 megabit, we were going 1,000 megabit, and it really made a difference. So we started selling this stuff, and it wasn't a standard. People like to buy electronic stuff that's a standard, so you can buy it from all these different brands all plug in together. Well, we'd invented it. It was what we called a proprietary networking strategy. And we were selling it all over the world. And our company got very big. We even got 200 resellers, and this one became our #1 reseller.
I'm dang proud of that, by the
Yes.
way.
Or so she says. Now, I
Hold
can't
up,
verify
hold
that. But at any rate, one of the customers that bought our technology was a university in Missouri. It's called Missouri Northwest University up in Marysville. And the vice president there came down and attended one of our training sessions, and he decided to buy some wideband gear, put it in up at Northwest. And then he came back and he said, "You won't believe what happened. I just received funding to hook up every single computer on our campus. Our dorm rooms, the computers the students have, the library, all of the classrooms. We're going to be the first electronic campus," as he called it, electronic campus in the world. And they did. And we built all of that equipment, and it worked flawlessly. And we had many, many, many other customers, and it was a very lucrative business for us.
It was.
But then, about 3.5 years into our success, the IEEE, which is the largest technical organization in the world, it's the Institute of Electrical and Electronic Engineers, decided they wanted to make a standard of gigabit networking. And of course, they invited me to be on the committee. So I went to the committee meeting, and there were 1,500 people on the committee. Have you ever been on a committee with 1,500 people?
This is madhouse.
It was kind of crazy to even get
Raise
noticed.
your hand, everybody can see you. No.
And you went to one of those meetings,
I
didn't
did.
you? Well, anyway, on that committee, I proposed that they use the way that we're doing it. And I had some patents. One was still pending, not issued. And they said, "Well, we don't want to build a standard on his patent. We don't want to pay him royalties." And I said, "Okay, I will give up the patent if you want to use the technology," because I thought it was more important that we have it. But they still, in the very first committee meeting, they voted they would not do it my way. They had to do it some way different than mine. And so, to put it in my own vernacular, they had to do it the hard way. But that is the story that we want to get into next time and tell you how Gigabit Ethernet came about. And it was one of the really fun challenges of my career, and a fun story. And I haven't said too much about it over the years. But I think it's time to talk about it, so we'll do that next time. But today I want to come back for a minute and just say, so we were building networking equipment that worked when nobody else's would work. And the neat thing about it is when you really loaded the network down, it didn't have collisions, so it didn't slow down. It's like the freeways kept at 70 miles an hour all the time. And if we could keep the freeways always going at 70, we get a lot more of that traffic jam cleared out. I remember in California, I was driving one day down the freeway, and it was going slow, it was kind of crowded. And these police cars were over on the side, and they pulled out in front of me, and they got in all 3 lanes, and they started driving, and then they started slowing down. And they slowed down to like 10 miles per hour. The freeway was probably going 15. So they slowed it down, and you could see the cars getting farther and farther and farther ahead. And then when there was a big gap, then they pulled out of the way and we took off. And they said this is a trick they do to try and get the freeways flowing again. Well, we did that to networking, and it really, really made a big difference. If you make a technology product that people need and that is dramatically better than what they have, well, then people are going to be very interested in it.
It was reliable, too.
It was
The
very,
wideband
very
was
reliable.
so
In fact, they
reliable.
said you cannot send a gigabit over a copper cable, over a twisted pair cable. And we go to the shows, and they say, well, it doesn't. I don't believe it works.
Yeah, you can't do that.
And so we set up a demonstration where we had a computer and we played video over the network, because no one could do that then. You can do that
Not
with
one person.
Ethernet. And we played this high resolution video, and people go, wow. They said, but you're only using a 10-foot cable though. I bet it wouldn't go very far. So the next show, we brought that wall that I showed you, and we actually put nails through the wire and all those things.
Yep.
And we even ran the signal over 8 strands of barbed wire.
Yep.
Just to show them that with that little equalizer, our signal was very, very good.
You touch those wires together.
You touch them and it would stop.
Yep.
You short it out, to prove that it was
a
working.
neat show.
A lot
Neat
of
technology.
people, amazing. It's written up now in a lot of college textbooks about, they even have the barbed wire security. One guy that I really have a lot of respect for, writing it up in his book, he says, boy, it looks like they've got a new form of security, barbed wire.
I know, yeah.
And little did he know, that was my next project.
Right.
All right, well, we're going to pick this up next week and get into the deep weeds of this thing, which are really a lot of fun. But I want to finish by telling you why I'm telling you this today. Because I think there is a message, even a lesson in this lesson that you can apply to your own life, to your own science fair projects, etc. I had a problem. I had a bunch of people using computers, and right when we needed the network the most, it shut down. It just basically went to its knees, and we couldn't get anything done. And so I said, darn it, someone needs to fix that. And I didn't know why it did it at the time. I just knew. And I said, I wonder if I can fix it. So then I studied what is the cause of the problem. And when I found out what the cause was, it turned out to be a lot more complicated than I ever dreamed it would. And I didn't know very much about networking at that point. And so I decided, okay, I'm going to figure this out. I'm going to figure out how to get rid of those collisions, because it was very clear it was the collisions that were killing it. And so I started reading, and I started experimenting, I started building stuff. I learned tons and tons and tons, but then eventually I came up with a hypothesis, a theory, an idea. And the idea was, how do you stop the collisions? Well, you accept everything that everyone transmits, and if the channel going out to everybody isn't clear and ready for it, then just store it in a buffer until the channel's open, and send it through. And that just seems so simple, and what a good idea to me. Then came the hard part. Remember, we talked about the optimism curve?
Yep.
On the front end, when I figured that, I said, oh, this is so simple. Anyone could do this. I could even do this. And so I decided to do it, because it's not going to be hard. As soon as you start really trying to do it, the optimism goes, because you start running into the problems.
All the problems.
Like, you can't send that bandwidth over a long distance because of the high frequencies are attenuated, or they're lost in the wire. Well, your greatest inventions are probably hiding right underneath your worst problems. If you have any problems, if there's anything in your life or in your world you don't like, maybe you should pick it up and look underneath, because that may be where you're going to make your big invention. And I think making little inventions is a great way to start. You want an example?
Yes.
I think they want an example.
I think we all do.
What about the toilet paper example?
Oh, I know where you're going.
No, you don't. I'm not going there.
You're not
I'm not going there. You stay out of this. Okay, don't listen to her. When you put a roll of toilet paper up there so you got it ready in case of an emergency, you can put it this way so that it rolls the top out, or you can flip it around so it rolls the bottom out.
Okay.
If you put it so it rolls the bottom out and it's dark and you can't see very well, you can't find the end to pull on it. So my hypothesis is that if you would turn it around and make it roll out the top, it'd be easier to find where the end is.
Oh, I thought you were going to do the other one.
That, I know what you thought. I'm not going there. I'm not making airplanes.
Oh, that was the one.
Anyway, what a simple, simple, simple little invention. And one day I went to this really, really fancy hotel, and they said, this is a 5-star hotel. And I went in there and I looked and looked, and I couldn't find the stars. But then I found out it just meant they do everything really fancy and really right. In other words, it's 5-star because they can charge you a lot of money.
Yeah.
But I went into the bathroom of my little room in this 5-star hotel, and when I went in there, they had the toilet paper turned so it came off the top, so it was easier to find, and they had the ends folded in so it's coming to a little point. You ever seen that done?
Yes.
And I thought, that's what makes it a 5-star hotel right there. Do you know that since then I've lived in a 5-star home? Yeah, that's what I do in my bathroom. I fold that in. And so if you ever come and want to use my restroom, you're going to see that. So, oh, look,
right there.
He's got a 5-star bathroom.
Wow.
But it's a little thing. It's about doing it right. It's neat. It looks tidy. And the best thing is when you're in a hurry and the light's off, you can find the end of it and get your business done. Find the problems in life and fix them. And when you do, you will be an inventioneer. And every time you solve a problem, it's going to make you a better inventioneer than you were before. My mission is to incentivize, this is a word that's going to be new to her, don't listen to her, jillions of inventioneers. Jillions. That's big. That's a lot of, but we have a lot of problems that can be solved. Many have been solved by the inventioneers that have gone on before. The science fair is coming up, so you'll have a chance to show off your inventions. And that brings me to the moment I've been wanting this whole night.
Okay.
And that is, at this science fair, I am going to be giving out the special award that we talked about last week. But I want you to know, I'm going to be looking for ideas that have potential, that I think have potential. And if you come up with an invention that really, really has potential, I just might want to invest in your new company.
What do you mean by invest?
That's where under your coat you put a vest, and you get in it, and then you're invested.
I want them to know what you mean, really.
Oh, you mean? Well, tell them what it means.
That means he's going to put some money up.
You're the one with the money. I really think that to really sponsor inventioneering, the best way I can do it is tell you how simple it is. You just have to be looking for problems and figure out how to solve them. And then I want to incentivize you by saying that if you come up with a good idea and it looks to me like it really has potential, I would like to maybe become an investor in your project. And I'll be looking for projects that I think have commercial potential to invest in. I want to see so many more inventioneers out of our audience, inventioneering.
Wow, that's big.
Yeah, I want to make the world a better place. Okay, well, we don't have time for R51 today, and I apologize for that, but we really can't show him anyway because this time of year he always gets weird. You remember what happened last year? In the spring, he always figures out some way of how to escape out of Area 51. He's gone again. He's gone? As we say, R51 is on the wind.
He's in the wind.
And if you happen to see him will you please let us know? He's been talking about fishing. He's all into sports. He's doing things like, if you see him, please let us know right away. Till then, I'd just like, in his honor, to take a quick look out and see if there have been any sightings. Okay, well, just keep an eye out for him. He could be
Is that time
anywhere. If you see him, call us. Okay, see you next time. Bye-bye.